Welcome to ES 310 Lesson 35. Today we'll start the last topic for this class by looking at vibration systems. These are dynamic systems that move in a regular manner either due to excitation or due to initial conditions. Today we will look at undamped vibration systems, and next lesson we will look at damped vibration systems. These are interesting systems because they occur all over in the engineering world. This is just an overview of this topic, since classes exist solely in vibrations and also in system dynamics, which is looking at these oscillatory motions and learning how to control them. So today we will look at undamped vibration systems and learn how to find expressions for the free and forced responses of these systems. Let's start with some definitions related to vibrations. A vibration is a periodic motion of a body or system when it is displaced from equilibrium. So like this spring, if we pull it downwards from its equilibrium position and let go of it, it will bounce up and down. This is an example of an undamped system, so it will continue bouncing forever because there are no losses in this system from friction or from air drag or from any of these types of things. So this is undamped. A damped system, which is much more realistic, is a system that the vibrations eventually die out in because of frictional effects. We also have free versus forced vibration. Free vibration is vibration that occurs because of an initial condition. So I may punch something and it will vibrate, or I could pull down this, give it an initial displacement, pull down this spring and let it vibrate. That is free vibration. Most free vibration in the real world will eventually die out because there is friction in the real world. Forced vibration is vibration due to an external driving force. Sometimes that driving force is a motor, for example, the vibration in a washing machine, or it's a regular displacement, like going over bumps in a road. These vibrations will continue for as long as the input continues. There's a number of quantities that we use to describe these vibrations. The first is the natural frequency. So any system has a natural frequency. That's the frequency of the free vibration. So if we give something an initial condition and it starts to vibrate, the frequency of that vibration is the natural frequency, which is omega n when you're talking about radians per second as your frequency. The period is the time per cycle. So if we started the stopwatch when the box was at the top of its bounce and stopped the stopwatch when it got back to the top of its bounce, that would be a cycle. And that time would be the period. A frequency is a cycles per second. It can be measured in radians per second, like natural frequency is, or it could be measured in hertz. Typically, if you're talking about a frequency measured in radians per second, it's given as omega. If you're talking about a frequency measured in hertz, it's given as F. And of course, the relationship between omega and F is simply, there are 2 pi radians per cycle. So 2 pi times F is equal to omega. The phase angle is the amount that the response is shifted at time equal to 0. So if we don't start at x equal to 0, we start at x equal to some other point, that can be translated into a phase angle, and it's measured in radians per second. And finally, the amplitude is the maximum displacement of an object. So if we're looking at this object and we pick the middle point of its stroke, somewhere around there, then it goes up a certain amount and it goes down a certain amount, and that amount is the amplitude, which is measured in the units of this displacement, so feet or inches or meters or whatever this displacement is measured in. Free vibration, as a reminder, this is due to initial conditions. We have an equation of motion, right? This is Newton's second law, hasn't changed. Sum of the forces equal to mass times acceleration. When we're talking about vibrations, we tend to write acceleration as x double dot, the second time derivative of x. We can rewrite this equation in its standard form for vibrations, so there's no coefficient in front of the x double dot term, and there is a coefficient in front of the x term. This coefficient, by definition, is the natural frequency squared. So if we can write this equation in its standard form, we already know what the natural frequency squared is. Now this is a differential equation. There are whole math classes on solving differential equations, and we're not going to get into that now. But if we can write an equation in this form, so we have a second derivative of a variable, some coefficient times the variable itself is equal to 0. If we can write this in the standard form, then x, which is the position, can be written in this form. All right, so whenever we write the differential equation, a differential equation is just an equation that involves a variable and derivatives of that variable. So in this case, we have the variable and the second derivative of that variable. If we can write the differential equation in this form, this equation describes the motion, but it doesn't give us an expression for the motion. This is the expression for the motion, x, in terms of things we know, and time, right? So the general rule here is if we can write it like this, then this is the solution. There are all sorts of courses on how to derive this solution. We're just going to use this form. We can find A and B by using information about the initial conditions. So if we know the position or the velocity at time equal to 0, we can plug in t equal to 0 into the position equation and the velocity equation, which is just the derivative of this, and we can find A and B, and we'll see how that works in an example. We can also write this expression in terms of an amplitude and a phase angle as well. And so if we're just rewriting this x expression in terms of c sine of omega n t plus phi, here c is going to be the square root of the squareds of a and b, and phi is the inverse tangent of b over a. Remember, phi is going to be measured in radians, so either set your calculator to radians when you do this calculation, or convert degrees to radians before you plug it in. The period again is 2 pi over omega n. Omega n comes from our standard form. And the frequency is omega n over 2 pi, or 1 over the period. We can also get to this standard form using energy methods. So if instead of writing the force equals mass times acceleration and the moment equals I alpha equations, we can describe our system using energy. We know that the potential energy plus the kinetic energy is equal to a constant. In a general case, this is our kinetic energy, this is our potential energy, but we sometimes have another term like a 1/2 I omega squared term if we have something spinning. We have possibly gravity, things of this sort. So if we know this is equal to constant, if we take the derivative of both sides, we have 0 on one side and the derivative of our expression on the other side. Every term in the derivative will have an x dot term. So for example, if we just had the 1/2 mv squared plus 1/2 kx squared, take the derivative, we end up with mx dot x double dot plus kx x dot. Let's factor out the x dot, which is on both sides, and since that's equal to 0, and we know that the velocity is not always equal to 0, then the stuff inside the brackets here is equal to 0. And that can then be written as our standard form. And then based on that standard form, we can find omega n, we can find our expression for the motion, x, we can find a and b and everything else. So let's use an example to see a little bit of how this works. So here is our mass on a spring again. We are told that the spring is stretched 200 millimeters by a 5 kilogram block. So that's our equilibrium position. Okay? So that will allow us to find K of the spring because it's not given. So at equilibrium, we have the sum of forces is equal to 0. That's the definition of equilibrium. It's not going to be moving. So free body diagram of this block, we have a force pulling up and a force pulling down. The force pulling up is going to, at equilibrium, be equal to K times x naught. That's our initial stretch of the spring, and the force pulling down is mg. We're going to define downwards as positive, because that's what the problem tells us to do. So then we can write our force equal to 0, sum of forces. We've got negative kx naught plus mg. So this tells us that mg is equal to kx naught. Now we'll do motion. So in motion, we're going to displace this block a little bit further down. So we've stretched the spring now. The force is going to be kx naught plus x, and the downward force is mg. This time it's accelerating, also accelerating downwards as our positive direction. So now we have sum of forces is equal to mass times the acceleration. The sum of the forces is negative kx naught minus kx, multiplying this out, minus or plus mg is equal to mass, and I'm going to write acceleration as x double dot. Now we know from up here that mg is equal to kxo. So that doesn't have an O. This term and that term are going to cancel each other out. And we're left with an expression. We can move this over to the other side. We have mx double dot plus kx is equal to 0. We need to write that in the standard form. The standard form has no coefficient in front of the x double dot term. So we need to divide through that by m. And we can write x double dot plus k over m x is equal to 0. Now looking at our standard form, whatever is in front of the x term, the non-derivative term, is equal to omega n squared. So the natural frequency for this motion is omega n is equal to the square root of k over m. We don't know k yet. We do know m is 15. Alright, let's figure out what k is. We can go back up here and use numbers in this expression to find k. So based on this expression, we have that k is equal to mg divided by x naught. Well, m is 15, g is 9.81, x naught is this, right? That's the initial stretch under just gravity. So 0.2. So k is equal to 735.75. 735.75. Plug that in down here, we get omega n is equal to 7. Okay, so now we have things in standard form. If we look back at the previous slide, we can now write the expression for the motion, just x as a function of time. So x is equal to, we'll use this expression, a sine omega t plus b cosine omega t. So x is equal to a sine omega nt plus b cosine omega nt. We're going to apply the initial conditions. They tell us that initially the displacement x is 100 millimeters. So x at time equal to 0 is equal to 0.1. And the speed, so x dot at time equal to 0 is 0.75. So at time equal to 0, x is 0.1. So x of 0 is equal to a sine of 0 plus b cosine of 0 is equal to 0.1. Cosine of 0 is 1. Sine of 0 is 0. So this will give us then that b is equal to 0.1. Then we go back and we're going to take the derivative of this. So x dot is equal to, the derivative of the sine is a omega n, derivative of the sine is cosine of omega nt, plus derivative of the cosine is the negative sign, so b omega n negative sine omega nt. And we're going to plug in x dot of 0, so a omega n times cosine of 0 minus b omega n sine of 0. This is 0. This is 1. This is equal to 0.75. So A is equal to 0.75 divided by omega n, and omega n is 7. So this is equal to 0.107. So our final expression then, if we go back up here and plug in numbers, is 0.107 times sine of 7, omega n is 7, t, plus 0.1, which is b, cosine of 7t. And that then is, in terms of the a sine plus b cosine version, that's our answer. In terms of the other version, right, the x can also be written as, let me create some space for me here. X can also be written as c sine omega n t plus phi. C was equal to square root of a squared plus b squared. So plug in 0.1 squared for b squared, 0.107 squared for a squared. We get c is equal to 0.147. And phi is equal to the inverse tangent of a over b. Plug that into the calculator and we get 47 degrees, or 0.82 radians. And those plugged in there then also gives us an equivalent version of this expression. But either one of these then is the motion of that box bouncing on the spring. Now, one thing I really want to point out, remember how we canceled these out? The spring and gravity? That will happen in any problem. All right? Any problem where you have a mass suspended on a spring or sitting on a spring, the initial compression or stretch of the spring will cancel the gravity term. And so the gravity term will always not be in our equation because it'll be canceled out by this initial stretch. So that's an important thing to remember. And that works either when we're using Newton's laws, or it works when we're using energy. So in general procedure, we draw a free body diagram, and we displace it a little bit from equilibrium, and we remember what we just talked about, that mg is going to always equal our kx, our initial stretch in our spring, and so those two are going to cancel out in our equations. Then we write our equations of motion. We use this to get rid of the mg term. We write that, and then we write it in this general form, right? So whatever our variable is, usually it's x, but it could be theta if we're looking at rotations, right? Could be y. Whatever our variable is, double dot, plus some coefficient times our variable. That coefficient is going to be the square root, or is going to be omega n squared. So we can always find omega n by taking the square root of that coefficient. And then we look at our differential equation solution. We write it in standard form. And that standard form is a sine omega n, which we found from up here, t, plus b cosine omega n t. And we find a and b based on our initial conditions, which means we may have to find the derivative of this expression if we were given information about the initial velocity. So let's take another example of this, and this time I'm going to solve it by energy methods instead of the Newton's laws. I could solve it by Newton's laws, right? Either way would work. You get the same expression, but I want to give you an example of how to do it using energy. So let's start by writing an expression for the kinetic energy of this case, right? So what's happening is we're pulling this block down a little bit and letting go, and it's going to bounce up and down as the pulley turns and the spring moves up and down. All right, this point, notice, is attached to the ceiling. So this point right here is our instantaneous center of zero velocity, which will come in handy in a second here. So we have the block moving up and down. So that's going to give us a linear kinetic energy, v squared. We also have the pulley moving up and down. So that's a linear mass of the pulley, v squared. And those v's are the same, right, because they're fixed together. Then we have the pulley turning, which gives us a rotational kinetic energy of I omega squared. So, how do we relate V to omega? Well, that's where the instantaneous center of zero velocity comes in. If this is a fixed point, the V is of this point here, which is also of this box down here. So they're related then by V equals R omega, because this is an instantaneous center of zero velocity. I, they give us the radius of gyration, right? So this is the mass of the pulley times the radius of gyration squared. And so we can plug everything into here, and we end up getting that the kinetic energy at some arbitrary point is going to equal 33.47 x dot squared. So you can do the math to prove that to yourself, but you plug in 50 for your mass of the block, you plug in 10 for the mass of the pulley, you plug in 10 times 125 squared for I, and you plug in V equals R omega for omega, and we should get this expression where x dot is just V. Now let's look at potential energy. So potential energy, we have the potential energy of the spring and the potential energy due to gravity. Now remember what we said, we always can cancel out gravity because the spring will stretch to balance it. That's true in energy as well. So we can write, so the only real potential energy we have is going to be 1/2 kx squared. Actually, let's call this S because it's not actually equal to the x we're being using, S squared. S is the stretch in the spring. X is the motion of this point 0. Those two are different. So we need to relate S to X. So if we look at, this is S here, and this is X there. If we use similar triangles, right, because this is the point of instantaneous zero velocity, we can use similar triangles to find the relationship between X and S. So if this is theta, and this is R, and that is R, our triangles then, we have x over r is equal to s over 2r. The r's cancel. We get that s is equal to 2x. Plugging that in, k is 1500. Take half of that, square the 2, you get 4. We're going to get a potential energy written as 3000 x squared. So our total energy, T1 plus V1, is equal to 33.47 x dot squared plus 3000 x squared is equal to a constant. We don't know what that constant is, but it doesn't matter. Alright, let's take the derivative. We take the derivative of the first one, we get 2 times 33.47 x dot times the inner derivative, which is x double dot, right, of the x, plus 3000 times 2 times x times the inner derivative x dot is equal to 0, which is the derivative of a constant. There's an x dot term in each term. We can factor those out and cancel them because we're equal to 0, and we're left with then that 66.94 x double dot, which is 2 times 33.47, plus 6000 x is equal to 0. Write this in standard form, right? So no coefficient in front of the double dot term. The coefficient in front of the x term is going to be omega n. X double dot is plus, divide through by 66.94. We get 89.63x is equal to 0. This term is omega n squared. All we're looking for is the natural frequency. So we just want to know what omega n is. So omega n is equal to the square root of 89.63, which is equal to 9.47 radians per second. And that is our answer. So we could use this, if we were given information about the initial conditions, we could use this standard form to write x is equal to a sine omega nt plus b cosine omega nt. But we're not asked to do that. All we're asked to find is the natural frequency. So that was free vibration. Now let's take a look at forced vibration. So in forced vibration, we've got a vibration that's caused because something is applying an oscillating force or an oscillating displacement. So the oscillating force we're going to call F naught sine omega naught t. The oscillating displacement we're going to call X naught sine omega naught t. This omega naught is our forced vibration frequency, and we're going to use that throughout this. All right, so a standard equation of motion, once again, no coefficient in front of the x double dot term. Coefficient in front of the x term is omega n squared. Nothing's changed there. But we have that equal to some form of this forcing function. So we have this d naught, the coefficient of the sine term, sine omega naught t, right? So the sine part comes from up here. This term will be known based on the variables in other places in the equation. If you have an equation written in this form, we can write the solution to this differential equation in terms of a free response, right? So the a sine omega nt plus b cosine omega nt, that's our free response, which we've already found. We know how to do that. And we do it exactly the same way as we did it before. Plus this term, which is dependent on knowing this, knowing our two frequencies, and then sine omega naught t. This term will dominate if there's friction in the system, right? Because if we give it an initial condition, if there's friction in the system, eventually it dies out, and all we're left with is this term. This term will continue as long as the forcing function continues. Now, something that's special about this forced vibration is we can get a magnification factor. So if you've ever heard of something being at resonance, this is how tuning forks work, for example, or the idea of if you're pushing someone on a swing. If you push at the right frequency, they get higher and higher and higher. You're adding energy to the system. There's this magnification factor that will magnify your input. If a magnification factor is less than 1, it's going to decrease that input, right? So if we define our magnification factor as the output amplitude over the input amplitude, so the output amplitude would be x, the input amplitude would be this x naught that's up here, then that's going to equal 1 over 1 minus omega naught divided by omega n quantity squared. If you ever take a class on vibrations, you will derive this expression. We're just going to use it. And the condition where omega naught is equal to omega n puts a 0 in the denominator, which equals infinity, right? So at resonance, MF is equal to infinity. Of course, in the real world, that can't possibly be true, right? Because there's friction in the real world. But in the ideal case where there's no friction, you can get a magnification factor of infinity. What happens then is usually bad things. Usually you want to avoid this point because things will shake uncontrollably and usually break. But that's the condition known as resonance. So let's take a couple of examples of forced vibrations. In this one, we have a block. It's attached to a spring, and we're given the spring constant, and we apply a force of 6 cosine 2t. And so this is a cosine term, so it's going to be moving back and forth, so this whole block is going to be moving back and forth. We want to write the expression for the motion x, and we want to determine the maximum speed of the block after the free vibrations dampen out. And we're told that initially the block is at rest and the spring is unstretched. And then we start this cosine 2t oscillation. So let's write, free body diagram. There's our box. We have our force here. We have our kx there. Gravity is downwards. Normal forces are upwards. And we're not going to worry about those because all of our motion is happening in the x direction. So let's write our sum of the forces is equal to mass times acceleration. So sum of the forces is, we're going to call this direction positive. So we have F minus kx is equal to mass times x double dot. So we can move things around and write it in standard form of mx double dot plus kx is equal to F. Divide through by m, right, to get no coefficient in front of this double dot term. That's our standard form. X double dot plus k over m x equals F over m. Now let's plug in numbers. We get x double dot plus k is 20. M is 20 pounds divided by 32.2. X is equal to 6 cosine 2t divided by 20 divided by 32.2. Right, so that's the force divided by the mass. Number-wise, then, this reduces to, this is 32.2. X is equal to 9.66 cosine of 2t. All right, so that's our standard form. We need our expression for motion. So that's our x. Remember, x is made up of two parts. We've got the a sine omega nt plus b cosine omega nt part. And then, so that's our free response plus our forced response, which was d naught over omega n squared minus omega naught squared times cosine omega 2t. Right? This part is just whatever the forcing function is. All right. So, first of all, we're going to look at our initial conditions. We're told that because x of 0 is equal to 0 and x dot of 0 is equal to 0. So we're going to, this is just for the free part. All right, so we're looking just at the a and the b part based on our initial conditions. So a sine of 0 plus b cosine of 0 is equal to 0. This goes to 0, this goes to 1, so b is equal to 0. Take the derivative of that, we get a omega n cosine 0 minus b omega n sine 0. I skipped a step in there, but it's the same as we did in the previous example. That's also equal to 0. So this is 1, this is 0, so a is equal to 0. So both of those terms are equal to 0, so x is equal to d naught, which was whatever's in front of our cosine or sine term here. So this is d naught. So 9.66 divided by omega n squared. Well, omega n is whatever's in front of the x term, the non-derivative term, squared. So that is 32.2. Omega naught is whatever's inside the forcing function. So that is plus 2 squared. No, minus 2 squared. So this is already squared, right? So 32.2 is omega n squared. Omega naught is whatever's in the cosine function. So then this is then times cosine of 2t. So if we plug these into your calculator, you're going to get 0.343 cosine 2t. We're asked about the magnitude of the speed. Well, this is the position. The speed is x dot is equal to 0.343 times 2 times the derivative of the cosine is the negative sine of 2t. And so that maximum x dot max is equal to 2 times 0.343 equals 0.685. And the units would be feet per second. So the key thing to notice here is once we get this in standard form, we have all sorts of information that we can find. So let's go back up here, look at our standard form. Right? Once it's in standard form, we have omega n, because that's the coefficient of the x term. We have d naught, that's the coefficient of this side of the term, of the forcing function term. And we have omega naught, which is the frequency of the forcing function term. So we have everything we need for this third term if we have it in our standard form. So let's take one more example where we use our magnification factor. So in this example, we've got a platform. It's sitting on 4 springs with a K of equal to 130. And the floor is vibrating. So the floor is vibrating, that's our forcing function. In this case, our forcing function is the displacement. It has a magnitude of 0.17, and it has an omega, so omega naught, that's our forcing function frequency of 7. That's in hertz. We need it in radians per second. So we're going to multiply by 2 pi to get it in radians per second. All right, we know we're going to use our magnification factor because we're being asked what is the output given this input. Okay, so determine the vertical displacement amplitude of the platform and the instrument given that the input is this 0.17. So let's take a look then at that expression. This is the expression we're going to use. So let's write that out just to remind ourselves. We've got x over x naught is equal to 1 over 1 minus omega naught over omega n squared. So we know x naught, right? This is 0.17. We know omega naught, that is 2 pi times 7. We do not know omega n. If we can find omega n, then we're done with this problem because then we can solve for x. So how do we find omega n? We have to write this equation of motion in standard form. This omega n squared is the coefficient of the x term. So this is free body diagram. We've got a box. We have 4 forces acting on the box. All of those forces are kx. Right? Because we have 4 springs. All of them see the same displacement. And we have mg, but mg is going to be canceled out by the initial displacement of the springs. So our equation of motion, sum of forces, is equal to mass times acceleration. All right, so our forces then are 4 kx's going up. The mg is canceled by the initial forces, the initial stretches of the spring, or compressions of the spring in this case. So we just have 4 kx negative is equal to mx double dot. So rearranging this, we get mx double dot plus 4kx is equal to 0. Make it standard form, so we want no coefficient of the x double dot, so we're going to divide by m. Okay, so standard form then would be x double dot plus 4k over mx is equal to 0. We know from our standard form that the coefficient of the x term is omega n squared. So if we plug in some numbers, omega n is the square root of 4 times 130, which is k, divided by the mass, which is 18 is pounds divided by 32.2 to make it a mass. This is equal to 30.5, and then we can plug that in up here, and we have x, which is what we're trying to find, divided by 0.17 is equal to 1 divided by 1 minus 2 pi times 7 divided by 30.5 squared. You put this into your calculator, you're going to get negative 0.93. So x is going to equal negative 0.157 feet. So this means, since this is less than 1, we are decreasing the vibration, which is usually what we want to do in this case, right? The floor is vibrating. We don't want our equipment to vibrate as much. That's why we put it on springs. So we're decreasing the vibration from 0.17 to 0.15. We're also switching the sign. So as the floor goes up, the equipment's coming down. And as the floor goes down, the equipment is coming up. But the magnitude is decreased.